Can you hear me in back? Is that fine? So I can get by without a microphone? Good. It's a great pleasure to be back in Stockholm and to kick off this new endeavor. What I want to talk to you about is an experimentalist view of perspective on testing field theories. And I'll show you with the CMB. And I'll show you what that means in a minute. And the reason this is a slightly different tack than you may have heard. Right? I know you've all probably heard at least 3 CMB talks. Right? So I'm going to assume you've heard those talks and that you remember some of them. And then I want to build on that and then tell you what's behind some of these claims that are being made, such as that we're actually measuring the spectral index or variations in the spectral index and scale and things like that. So let me start just by giving a little background. This is the Microsoft view of the universe. And here is the pie chart. And I think the amazing thing, and it just never ceases to amaze me, that virtually all cosmological measurements, regardless of how they're made or their redshift, near or far, so whether you reduce things nearby from far away from the edge of the observable universe, agree with one model. And these are a breakdown of the contents of the model. And just that alone is just a phenomenal statement. And what that model assumes, and I'll get back to this, is that a flat geometry, simple model, and we can test that at a couple %. We'll get back to that. Then it's got some new form of matter, and we know that depending on how conservative you are, something like 15 sigma level. If there's something that mimics the cosmological constant, and other speakers will address that and exactly what it is or how we should be thinking about it. And whatever it is out there, it's many, many sigma. And what I'll focus on a large bunch of time is that there's a deviation from scale invariance. And by that I mean that this is the power spectrum of the matter power spectrum as a function of, get back to this, as a function of wave vector here. Scale invariance is ns equals 1 in that. So it just goes like K in this form. And that's seen at about 3 sigma. I think another thing to point out here is since this we need theories to understand that. What we don't know is huge, right? What is this dark matter component here? Why is there that breakdown? That's still phenomenological. But, so, who knows? You guys will be, people here will be telling us over the next little while. Along the lines of connecting back to more fundamental theories is we can compute that from Big Bang nucleosynthesis, right? So there's this tension now between what we know phenomenologically and what we can understand from perhaps a deeper, more fundamental level. Let me just, it's bad to just show slides with a bunch of numbers, but let me just quickly here, it just is the model in more detail. By the way, please, there's a few enough people who have questions, just let them out. So, this is the model from just the cosmic microwave background, and it's again assuming flatness, show that in the middle. And this is adding most all the other data sets, like other measurements of microwave backgrounds in WMAP, in that map on the first page that you saw. The supernova in there, the Sloan Digital Sky Survey, or the 2DF survey, the Luminous Red Galaxy Sample. You'll hear more about all these things in the rest of the conference. And you can see there's not a big difference between both of those. It's good. Well, actually, the main difference for factors of 2 and error bars comes from nailing down the mass in the mega matter or mega matter H better from these other surveys. The parameter that I'll keep, and this is the most conservative take on WMAP, if you will. The parameter that I'll keep coming back to is the scale of spectral index, and I'll talk more about it. But just to note the significance. With just WMAP, it's different than at about the 2.5 sigma level from scale invariance. And I remind you that notion that scale invariance was an observation. It was a phenomenological observation. that now that it was 1, and we're now starting to see that deviation. The main point here is that as you add more data sets, the significance just improves, and in fact, it actually deviates a little further from 1 than you get with just the WMAP data. Sure, just help.
So I guess
I'll get there. Okay, I'll get there. Okay, so cool. The other thing to note here that I'll keep coming back to is tau. What is tau? It's the optical depth. It's the integrated number of free electrons back to the decoupling surface. Okay, and it tells us how many of those microwave backgrounds are scattered. And then the overall normalization here, the Hubble parameter, the physical matter density, and the physical baryon density. So that's the background in which I'm going to talk about this. And just one more background slide, if you will. I think this puts this, for me anyway, this puts the simple model in perspective into how to think about it. And that is, in a sense, the microwave background is just a surface out there, right? We can put that surface in different places, right? And there's this degeneracy, right? We can put it nearby and change the geometry. So here's a plot of omega lambda on the y-axis, omega matter on the x-axis. This is the line for a flat universe. Make it totals 1 when you sum up all these. And the microwave background doesn't tell you that the universe is flat. It says that you live along, and this is a term from Mustafi, this geometric degeneracy there. And how that's encoded is that, there you can see, if you change the Hubble parameter from 30 kilometers per second to make a parsec here, which is, if someone told us that the Hubble constant is 30 kilometers per second to make a parsec, we would just say the universe is closed. Everything else in all these plots would be the same, right? But it's not. We say other observations tell us it's near 72 or 74, something like that. That singles out flat. So instead, what we do for all the analysis is we assume it's flat. And we assume flatness to derive these parameters. And the best fit to this model is fantastic. Right? The best fit to this model has a reduced chi-squared of 1.037. And that's with 3,162 degrees of freedom. Okay, from the power spectrum and the pixelization of the map. Right? That is an excellent fit. So the model does very well. Okay. So what do I mean by testing specific field theories? What are our handles on them? And there are 3 handles that we have, and unfortunately there are many more theories than experimental handles. So this is what we're going to have to live with for the next while. One is the spectrum of fluctuations, the scalar spectrum index I keep talking about and we'll come back to. Does it change with scale? Does it change with wave vector there? That's one, and we are on our way to doing that. Showing that. There are also gravitational waves. Are we going to see remnants of gravitational waves from the early universe? The universe is kind of around 45 seconds. And is there any non-Gaussianity? So I'm going to run through these and give you, in some cases, a new perspective on what we know, what we really think we know about them, and what we have to know to make progress. Okay? I should point out that the notion of that the deviation from this phenomenological value, the Harrison-Dover spectrum, I think that is Slava here somewhere. There he is. So, I think the first paper on this was Konov and Kubizov in 1981. And it's just now gives an idea of the time between theory and actually seeing something. We're just now starting to see that. Okay. The types of, just to make sure we're all on the same page here, when we talk about these perturbations, especially those first 2 items, we just divide them into 2 classes. They are either sourced by scalars, with the change in density over density, and this is that matter power spectrum I showed you earlier, and that's the index we keep talking about. Or tensors, the gravitational wave strain. These strains are huge. 10 to the minus 7, right? LIGO, for instance, or Lisa looking for 10 to the minus 20 strains, right? These are huge strains that we possibly see from the universe, and we will quantify that with this parameter R, which is the variance of the fluctuations in tensors over the fluctuations in scalars. And depending on which series you pick, it should be about 0.3 or less. Predictions all the way, and there are some predictions higher than this, many predictions less. I think many would argue that the simplest predictions are around 0.3. Let me just mention it, right? The scalar perturbations produce temperature fluctuations in microwave background. E-mode polarization, we'll get back to that. And the tensors produce temperature fluctuation, E-mode polarization, and D-mode polarization. If there's questions in the end, I can show you a little tutorial on at least how I think of the difference between them. But for right now, just think of them as a decomposition of a vector field on the sphere. This one is analogous to the electric field and then magnetic field. So the big thing is that these theories of the early universe, right, at 10 to the minus 35 seconds, make predictions about these that we can test. Okay, before getting to actually just looking at what the data say about these and how to think about them in terms of the power spectrum, I just thought it'd be fun that this is for a project that we're doing with Jim Peebles, so just to scroll through what we've learned about the spectrum over the last few years since the microwave background was discovered. This is the anisotropy spectrum. So what we've done is taken all the measurements made in the microwave background, put them all on a common footing, and compared them to where we are now. So this is the state, between 65 and 1979. This is the current spectrum right here. And you can see many of your favorite experiments. Let me just, there are no calibration errors in here. These are just as reported. Let me just go through the spectrum here, and you can see some interesting things we thought we're using. By the way, these gray boxes here are average of the previous transparency experiments, so you can see how things have evolved. So this was before the anisotropy was discovered, celebrated here last year, and you can note some amusing things. Look at all these. This is the quadrupole was detected down here and then refracted. Look at all these fantastically small error bars at large angular scales here and at small angular scales. If any of those teams, had just looked at intermediate angular scales, they would have detected the anisotropy. They had the techniques, they had the sensitivity, right? They just know and don't. It's an amusing thing. We can go on. This is what it started to look like. Here's the DMR discovery there in the early 90s. This is starting to fill out. Again, the boxes are the previous one. We start to see some detections. Here, again, through the mid-90s, you can start to see that there's some shape in the power spectrum. These data are starting to show up here in the mid-90s. It's improved up here. Here is the jump from the new millennium, the great jump in sensitivity. It's filled out. Now we're really starting to see spectrum out here. There's still, those are still consistent. Actually, taken together, they start to see humps individually. The boomerang and daisy are consistent with flat here. The paper is written by many of you showing that, but you can really see now this is clearly seen, very clearly seen, going on in 2003. Now the second shape, the second peak area is in really good shape. And you can see here, this is the first year WMAP data, and these boxes are the previous averages. So this is the last jump. So it's just been this great, the field just evolved over these years, from 65 on, the last 40 years. And it's just evolved steadily, right, to this precision and accuracy that we now have. So let's look at the spectrum, the most recent one. So here is, again, of course, the multiple on the x-axis and our y-axis. And This is the most recent WMAP, which is still a 3-year release. Experiments at higher L from our colleagues. And when we talk about the scalar spectral index, what are we talking about? In terms of this spectrum, I mean, what does it mean? For many people, it's just a parameter that's in the model. What it is it's just the overall slope of this power spectrum after you take out the acoustics. Take out the acoustics. And how does that relate to inflation? Well, what's driving this are fluctuations in gravitational potential on those angular scales. What's driving that the second peak here are fluctuations on the finer end of the scales. These come out earlier in inflation. These come out later in inflation. So we're seeing the process of these, if you want to think of it in terms of inflation through looking at this index, through looking at the slope of this spectrum. So that slope is our experimental handle on these theories of the universe. And again, just to say, you need a model to predict that, right? To say what it is. It's a really neat thing. It's sort of this new generation of cosmology. Okay, so now let me tell you, so that's what we're after, right? The overall slope in that spectrum. Let me tell you why it's hard, and why when you just see claims in literature, what you should be asking. This is the same model with 3 different spectral indices, all between 0.96 and 1. And remember, we're looking for deviations from unity here, right? The black line is the best WMAP plot. And you can say, well, that's a huge difference. You can see that. You should be able to see that easily. But let me just show you what's going on here. It's not quite that simple, because if I just scale them so they all match to the first peak, which is just saying that we don't know the overall normalization, which is the parameter sigma 8, I get this plot. Right? And they're much harder to distinguish. Now let me tell you the next thing, is that in determining all these things like this, the key parameter, the key instrumental parameter, this is really the crux of an experimental perspective on this, is you have to know the beam response of your instrument. It's critical. And it's true for the optical measurements, the lensing, for everything. So here's a picture of it. This is the Fourier transform of the resolution of not WMAP, but something with the resolution of twice WMAP. Right here. And all I've done is take and plotted the response and vary the full width half max of the beam by 1%. Right? So this is the instrumental response, varied by 1%. And the reason I'm going to take that is because there is no, you won't find any other experiment out there that has besides WMAP, that can claim anything like this sort of precision on the beams. Now what I'm going to do is divide those spectra again by that variation in the index. And you can see that they fall almost on top of each other. So the lesson in here is that to tell these sorts of things, to tell things like you have to, like that the spectral index is really different than 1, you really have to get into the heart of an experiment. And you really have to look at it in detail. It's not just adding a bunch of experiments together. It's correcting systematic errors and how they propagate through. And that's something we spend a lot of time doing. In fact, we put more, this solving for the beams, I think, is the hardest thing we do. We can get all the cosmological parameters for all models and all mixtures of data in about 2 weeks. We've been working on the beams for 4 years. To give you some idea. And in the past year and a half, it's been amongst all of our CCD technical. So it's tricky, and that's one of the things that takes so much time. Okay, so that was an experimental challenge to get the index right. There's a second challenge, and that's what we call an astrophysical challenge. Right? The first stars reionize the universe. Right? That's a redshift is something like 10. And those create electrons. And what they do is they rescatter the microwave background, right? Putting diminishing the height of that, say, the first effect, the whole spectrum there, and they also polarize it. And the thing is, that first one can mimic the change in the index. So you have to get that right. This is so-called the NS, the scalar spectrum index tau, with the number of electrons degeneracy. So we have to get that right. You can't tell anything about the scalar index, i.e. about you can do models of the early universe without knowing the optical depth. And so what we do is we measure the polarization to tell that. And let me just give you a brief picture here. So ignore the blue stuff now. I'll get back to that in a minute. This is just to remind you, here is the temperature anisotropy up here. Here are measurements of this is the temperature, polarization, and correlation. These are the E modes that I spoke of earlier, of the polarization, that particular configuration of the polarization field on the sky. These are measurements by colleagues at finer angular scales. The signature you need is you have to look down here at large angular scales, because reionization has happened later, right? It happened in redshift or something like 10, so you have to look at large angular scales to get it. You look down here, and the height of that peak right there, so-called reionization peak, is proportional in this plot to the optical depth. All you do is measure the height of that peak. So the experimental is going to be just measure the height of that peak, read off the optical depth, break that degeneracy. So we do that. Here's actually what the data looks like. So it is just the deviation of those highest multiples, lowest multiples, highest angular scales, from 0. That is the signal. And this plot is proportional to tau squared there. Here's the E mode signal. Here's the B mode signal. Foregrounds don't know anything about E or B modes. They contribute equally, right? So the fact that there's no signal here, there's a signal there, is some assurance that we're not, there's some assurance that we're actually measuring something that's there on the sky. And the other thing you may have seen here is we have to, at some level here, we have to start the foreground emission at the 50%, depending on L, to a factor of 2 level. And we'll come back to that in a minute. Okay, so that's what it looks like. Here's the plot then. N sub S versus tau, the optical depth. First year with external constraints getting down. What it did was it took a measurement of the polarization to break that degeneracy. And what you can see is that once you know that tau is low enough, there is no degeneracy right here, right? There are no bananas down there once you know that the optical depth is low enough. So either measurement or limit is what allows us to constrain the scale spectrum index. Here's a plot of it in a slightly different way. This is the likelihood versus the index here for just the basic 6-parameter model. We can play with the Snežo-Hilbert distribution. I mean, that's I think a fine point I'm not going to worry about. But you can see we're looking for deviations from 1, and that's the significance there. Let me show you another way. So this is getting back to Ruth's question. That's with just the 6-parameter model, what I've showed you. If we now say we want to test, say, a specific model of inflation, and we add R, we add the tensor component, see how well we can constrain it. We work in this 2-dimensional space. And now you can see, so here's the phenomenological model, Harrison-Zodovic's model up here. And now many people look at this, or I want to show them both, and say, that looks like 2 sigma, how can you say it's 2.5 or 3 sigma? And the reason is this is a 2-dimensional likelihood plot. The delta chi-squared for that line in 2D is 6.17, right? And the square root of that is the in 1D, the square root of that is the number of sigma. And you can see it's somewhat over 6.2. Okay, so here's what it looks like if you add tensors in, and this is true in general. Like if you make any deviation from that simple model, when you add components, the constraints on the scalar spectrum index are going to deteriorate, right? We're not going to be able to say that it's different than 1. And that's just the state we are right now. We need more experiments. Here are various inflation models that we not go, others can talk about, but we're not going to. Okay, so what do we need then to really to describe the data? We need an optical depth. Okay? And this is, we just take those 6 parameters and drop one and ask, how good is the model when we drop that one? We need an optical depth. This is, and that's the square root of that is the number of sigma, 2.8 sigma. We need that scalar spectral index not equal to unity, that's delta pi squared 6 right now. In the original release, we said it was 8. Some work by Erickson said that we hadn't extended our likelihood formalism up to a high enough L. We did that. Work by Huckenberger said that, well, they disagreed with our source correction. We compare those, and both of those drove it down a little bit. We need dark matter, and that's our key. The square root of that's where the 15 sigma number comes from. Without dark matter, you can't do anything. What we don't need, this is now adding another parameter, does not improve the fit significantly. Right? We don't need that running, we don't need that alpha parameter. We limit that the change in index to K to something like 5% effect. We don't need R, we only get limits on it. Right? We can't tell it in the gravitational waves. Massive neutrinos, we can't tell that, we can only limit them. Okay, we can keep adding parameters, but it's just, once you add a parameter, right, your constraints on the previous ones are lessened. All we need is the 6. And so that's from an Occam's razor point of view, that's what we've done. 6 parameters to 1 to 5. Okay. Yes? The tau is, that's good to find. The 3 is there, right? Right. Yeah, it's fine. Okay, so that's, the tau is completely driven by that, measuring now. And in fact, you get, and you get a greater significance when you get, the tau, in fact, from the data, if you just look at the polarization of the effect of the tau, is greater significance than you get when you do the full model. So what happens is the tension between the other parameters want to slide the tau around a little bit. Okay, gravitational waves. So now this is the same plot as before, and these we have we've computed that we should be able to detect them if they're at the 0.2 level if we run judgment math for 12 years. So we're not there yet. See if NASA allows us to get there. But here's the spectrum we're looking at. Again, just to give you the lay of the land, right? This is from reionization, that peak there. This is from the horizon side at decoupling, that's that peak there. This is a term from lensing. So from lensing, gravitational lensing of the E modes, produce this term there. So gravitational B modes at these larger angle scales are not primordial. They're not, we can't probe them with primordial in some sense. They're not really tests of field theories of the early universe. And the thing I want to point out, just make 2 comments on this. I mean, this is all of us in the field, I think, are going after measuring these. Right? It would be great to get another handle on this. This is on the early universe. This is the level of foreground emission for large angular scales. It's extrapolated here just because it includes a large fraction of the sky. And you can see that measuring very small values of the B mode spectrum is going to be difficult. Okay? Completely doable, but difficult. It's going to take the stability of the space mission, we think, in the end, to make a definitive measurement. But there's hope. And I should say the foregrounds in this I think the least challenging aspect of measuring the beam image. So we have two peaks. Here is a zooming in on the foregrounds. If you just look at a small patch of stuff. So what I want you to focus on here are, now here's the same line in the end. So this is an R of 0.3, the same, roughly the same opposite that seen from W map. Here is a much smaller tensor scaleration. I think even the Theore's colleagues can tell you, right, if R is not near 0.3 or 0.2 or 0.1, something like that, then I mean, that's the simplest expectation. That's the string theorists where you say, oh no, it can't be that high, it's got to be 0. But I think sort of the simplest high expectation value, if you will, is up near there. If it's not there, it can be, who knows where it is. So we really want to see if it's that high. There's hope with foregrounds at these intermediate angular scales. This is the level of foreground emission at 150 gigahertz. And you can see it's well below the level that we expect from these primordial levels. So it should be at intermediate angular scales that we can measure this without worrying about foreground emission in first order. Of course, you then have to ensure that it has the right spectrum of that frequency. But in terms of finding something, it's very promising. There are a lot of people who are targeting this region. This dashed line, the boxes, are just a made-up mission that you can do from the ground. This gives you the idea that, indeed, with feasible systems outlined here, it's very it's straightforward to measure in terms of technical. Okay, so that's all I'm going to say on gravitational radiation. We're all going after it, and you'll be hearing about it over the next few years. Non-Gaussianity, so the other handle. So this would be fantastic if we could detect something primordial with non-Gaussianity, because that would truly limit the number of theories talking of it to choose from, go up and down, or help select the right one, how do I phrase it. So where do things stand? The quadrupole, so this is just a list at the top of the list. The quadrupole, even though you still see it in the literature, is not anomalously low, period. Okay? It's just fine. For the full sky, so the other related thing, the full sky, the 2-point correlation function is not peculiar. This is something we called out that it was peculiar in the first WMAP release. And with more analyses, we have seen that that is not the case. We look at the full sky, it looks just fine. It's got a 12% probability to be consistent with lambda CDM. So I think there's nothing really funny here. All detections of non-Gaussianity are based on a posteriori statistics, which is really important to keep in mind. Is that you seek some oddity in the map and then try to find some way to quantify it. And that's it just doesn't, even though the significance of some of them is they're around 3 sigma, even though the significance of some of them is as significant as, say, the departure of the scalar index from unity, they have a completely different kind of. It is, I think it's amazing to us who are making these maps that there's so little weird in the data. No matter how you search, we have to look really hard to get something that looks funny. The north-south asymmetry keeps coming up, and it's weird. I'll show you it in the next slide. And that's visible in the Kobe data. This is not new. And just to reiterate, there's no, although we tend to, from WMAP, try to restate these and emphasize them, right? We would love to find some clear signature of cosmic non-Gaussianity, because it would be so powerful. We have, no matter, for all the tests we've done, and we've done a fair number, we have not found it. Looking at the tri-spectrum, the bispectrum, the Minkowski functionals, all those sorts of things. So let me just go through and show you where things stand, what's going on. This is a recent paper by Amir Hajan, showed that when you actually include the full sky, so the two-point correlation function doesn't tell you to use the cut sky, but when you include the full sky, right, which does call for some model of the foreground emission in the active plane here, that a significant fraction of the quadrupole intensity is in that region and in that region. Okay? And that's what's, so the question becomes, if we have corrected those two regions correctly for foreground emission, then the two-point function is not weird. So it's an experimental question, right? That's it. And we have in the two-point function is fine. Alignment, Max is here, will be here, and I'll let him talk to you about alignment. Lella and Cruz pointed out an especially cold spot down there, which we see and agree with, that it's there. The level of significance is, well, here. Something, 1 to 2%. So a little funny, but how funny it's if you look for the closest to the hottest thing in the map, you're going to find it. This is well away from foreground. The fingers that we talked about, the north-south asymmetry, and we've been talking about this for years, right? It's that basically, you can see in the south, there are these fingers, right? It's a much different structure than in the north. That's the north-south asymmetry. That's the root of it, right? And that is just, until there's some ocular reason, that's just the sky we've got. And it's not, that's not, again, not new. It's old. And Kobe, and I think my favorite demonstration of non-Gaussianity is, this is now the 3-year map, is that the detection of Stephen Hawking's initials persists. Right? So if you had an a priori theory that predicted little s's and h's in the map, you would have detected them with very high likelihood. Right? But, so this is just an example of how I think tricky and how important the notion of a posteriori is. Let me just end on the non-Gaussianity with some plots here. So these are plots now of the distribution of the temperature as a function of frequency, as a function of resolution. So that plot's the same as that one. This is a plot of the resolution of the map, so getting it up into different pixels. This is the distribution, accounting for the fact that there's different weightings in each frequency. The red line is a Gaussian FFT distribution. This is just the 1 point. And you can see it is excellent everywhere. This is the cold spot. It sticks out there in the course's beginning of the data. So it really, yes, they're very important findings that we've got in, but you just have to be very careful. Okay, let me just take another couple minutes here. I want to show 2 things to bring you up to date here on what's happening. So what's next? So I just ran through, right, the scalar spectral index. We see no running, gravitational waves if they're at a high level or around the corner and eminently effective. They support your local CMB proof. Right? And non-Gaussianity, you've got to keep looking for it and get better and better tests, and hopefully that the theories can make predictions that we can directly test. But I don't think we're there yet for any simple one. So now let me just look towards the future. What's happening? Well, of course, here are a lot of ground-based experiments. Here are a series of polarization experiments. This is something we're going after spread around the world, going after the B modes. But there are many people here who know much more about it. And I think that would be fantastic for testing all these things, possibly even detecting B modes, certainly non-Gaussianity, and many things. It would be fantastic mission. What I want to focus on for a minute here, a couple minutes, is just the ACT project, which I'm involved in. And the next frontier, which we're talking about, are the polarization. But also, to get at these small angular scales, we want to look at, one way to get at them is you want to look over a larger basis. an angular scale as you can. Okay? Because then you just get a longer baseline, and since you're looking for a slope, the longer baseline helps. And we think we can get down to a percent level accuracy we hope to by the end of 2008 to give a benchmark. Okay, so this is this project. I'll just go through this quickly here. There are many collaborators, and there are over 15 institutes and 5 countries, and in the U.S. the hard thing is 3 governmental groups. And the idea is we're starting to look at the sky, not only with a microwave background, but coordinating that with a large theory effort to small angular scales, optical measurements from Chile and South America, South Africa, with X-ray observations, and all these groups are getting together with UV observations from galaxies to target specific regions of sky, so we can really get the whole region from the surface of glass scattering, upward surface down to us. Just build that picture out, multi-wavelength, but all after the same thing. You'll hear about the science you can do over the next course of the conference. So here's our effort. This is we built this new telescope, and it is now down in Chile at 17,000 feet. And this is built in Vancouver. This is why we don't observe in Vancouver. And we have that. It's coming along line, and this is another way of another example of a large number of groups getting together to do this. Is we're now building arrays of bolometers. And so here's this idea. This bolometer concept came from Harvey Mosley's group at Goddard and Ken Irwin's group at NIST. The idea is that we make arrays of bolometers there and cloud them. So we're really approaching almost like a CCD type image concept of looking at the sky in millimeter wave radiation. Each one of these bolometers is about, or can be, not quite yet, is about as sensitive as one of the bolometers, say, that gave rise to blue wave. So this is what's coming down the pipe, right? And this is just one example. There are a couple of starting to have systems akin to this, but this is Goddard, and this is NIST. Our electronics are based on Scuba 2 electronics that come from our Copland group in Canada, and we started observing with this system, and we just got our first layout the other day, and so we're all very happy. And this is a map of Jupiter, now down to arc minute resolution, and we should be able to use that arc minute corresponds to L of something like 8,000. Right? So we'll really be able to get a good baseline to go after things like the scale spectrum index. And so we're very happy about that. And so looking ahead, you'll have that. The South Pole Telescope has a similar system, or conceptually similar system, and in that conceptually in that they're going after the finest angular scales with a large array of bolometers, a much different array of bolometers stuff. And they've also seen first light. So really over probably the end of this year and next year, we should start to see results coming out of these. And now let me end here with the last 2 slides of sort of the ultimate experiment. And this is from work this is a senior thesis that we just did. One of the things you can ask, in a microwave background, since we will have measured it really well. This is a Planck-like quality measurement here. We will have measured it really, really well in the next few years with huge angular scales and enormous sensitivity potential. And you can ask how it will evolve in time. And this is a movie, right? So as we sit here, right, we think about us here looking out at this surface of glass scattering, this decoupling surface out here, right? And the universe is populated with gravitational potentials. And this photosphere, as the universe ages, this photosphere is expanding out through these potentials. So the surface what you see is the microwave background has to change in time. Okay. Actually, it only changes usually at small angular scales. You'll see what happens. So this is a movie of what the microwave background sky should look like. This is a movie of what the microwave background sky should look like as we go out these n billion years into the future. I think this just goes up to 10 billion years in many cycles. And so the picture to take is that there are these wells out there, and our photosphere is just moving through. And you can see other neat things, and that the largest angular scale fluctuations there get enhanced. So this is the late time Cambrian Sachs growth effect. They get enhanced where the small ones can plow through, the large ones get enhanced, and it looks, as far as we can tell, we've looked out to about 100 billion years, and we see that they're persistent. So these guys, so the small scales will go away positive time. The large ones are going to be around for a very long time. We're still trying to find that. And so it turns out, for an ambitious society, that you can actually measure the expansion of the universe through measuring the change in the pattern of the microwave background. And here's all you need. This is why you really have to support your microwave background group. Here is the power spectrum in red of the difference in two maps of the microwave background taken 100 years apart. And here are the error bars for an experiment with just a 3,000 by 3,000 wave detector. So I showed you we'll have 32 by 32 in less than a year. So this is still 100 dimensions, so maybe that takes 20 years to do. And then you just make these two plots, these two pictures over 100 years, and we can actually measure the expansion of the universe by measuring the change in the massive background. For perspective on that, going back to where we've come in 40 years, actually this requires a jump in technology roughly equal to the jump between 1980 and now. Let's just go now to 20 years in the future in terms of sensitivity to the technical. So that's what we think about when we're not at the scale of spectrum index. So let me end there. Thank you.
Any question? Please say yes.
Does your review from the series depend on your assumption of that universe?
If we let that go, then many things change if you let that go. And the only way you get it back is by probably if you added something like baryon oscillations. I've just forgotten the number, but yes. Yeah, if you add, pretty much it goes, you lose that if you add any other parameter.
Yes, please, Mark.
How do you calibrate X so that you have overlap of the map for the semester,
We're going to calibrate on WMAP. So it's just a matter of going to large enough annual scales. And it looks like we can do that. That's one of the things. That's one of the things we worry about. So the strategy actually involves going deep and then going wide to overlap with WMAP. There's another reason why we need WMAP going for 12 years. Right? We will calibrate all these ground-based experiments. No, we can do it, but we'll have an 8 years. The longer we go.
To get a nice map like this, you have to subtract a lot of galactic programs.
Right.
And there is a paper by Pinkfine who claims that by doing that, it finds evidence for something else in this WMAP spectrum. Could you comment on that?
Sure. I mean, it's so just so the question is when you to get a map like this, which is foreground clean, right? I don't think I showed the raw data on here. You have to take a model of the foreground and subtract it. When you do this, Pinkfine and colleagues find a haze around the middle here in their foreground line. And that haze comes from decays of who knows, particles in the center of the galaxy, and it would be, and the question is, how robust is that? Are we seeing the radiation from particle decays in the center of the galaxy interaction? And how to subtract the foregrounds, the level at which you need to is still actively debated. Now, I guess what's the first? It would be fantastic if true. It would be wonderful. I think it's still so fraught with peril that it's nice now. It's not certain by one way. It's intimately connected to the question of is there spinning dust? Spinning dust has a peculiar emission spectrum. It'll have no bearing on anything that I've shown you today, but it does have bearing on how he finds this extra part. And so there are many components that we don't know about, and I think he's on the borderline of what we know we don't know. So,
Yes, please.
That aspect of the other systematic aspect, you know about the quote here, do you think that the quote having and the possible parameters?
Yeah. Yes. So what they include, so we have an overall calibration error, which is 0.5% right now. They include that. There is the largest error by far in all this is the error in the beam, and that's propagated all the way through. And then there are things like nuisance parameters, which I didn't show you, things like the possible SZ contribution. That's included. Point cloud structure, that's included. Galactic modeling, that's included. All those are included in the airball.
We have a last question there.
Actually, I say that I think the biggest challenge to measuring that is not going to be the technology, even though it's fantastic. It's going to be the point sources fluctuations in the point source, which will have nearly the same spectrum. And so, like anything with the CMP, right, the quick answer is you just measure the multiple frequencies to subtract photons. But more nearby, we have we see and you know somebody can publish this. We haven't had a time. Is when we take maps from year to year, we see differences from the foreground, and it's primarily and I say primarily that's the only one I can never see visually is recency sources taking. It's really clear. And we should publish that or somebody else should publish that.
Okay, thank you.
Thank you.
And so now the next speaker